Hello, welcome to Inside Track at EmTech Digital, your inside look at the coolest and most cutting-edge tech coming out of MIT. My name's Neil Firth, and I'm the news editor at MIT Technology Review based here in London. So, today's speaker is someone who's getting to grips with what it makes up me, you, and the entire universe. Phiala Shanahan is a theoretical physicist at MIT's Department of Physics and was named one of Science News' 10 scientists to watch last year, as well as many, many other awards and honors. She uses machine learning and supercomputing to probe the heart of the standard model of particle physics for its secrets. She looks at the smallest objects we know, the fundamental particles that make up our world. Understanding how these particles interact, decay, form, could give us new insight into things like dark matter and other mysteries of the cosmos. These particles are extremely hard to manipulate and study, and the computational demands of doing so are huge, even with the world's best supercomputers. So Phiala leads a group that is using machine learning to do some of that heavy lifting. She's shown how incorporating physics with machine learning can speed up her work and might just help her explain the universe a little bit better. Phiala, it's great to have you with us.
Thank you very much. Okay, so it's really a delight to be here today to talk a little bit about what machine learning can do to help us understand the structure of matter at the most fundamental level, and also about what special features we need in our artificial intelligence or machine learning algorithms to really exploit it for these sorts of problems. Thinking about the structure of matter, our modern understanding is that all of the visible matter in the universe is made of atoms, which are of course inconceivably tiny, and despite their name, the Greek origin of the word actually means uncuttable or indivisible, our modern understanding is that atoms actually have deeper layers of structure. At the core of an atom is the atomic nucleus, made of protons and neutrons, and the protons and neutrons in the atomic nucleus themselves have a substructure. They're made of matter particles called quarks, held bound tightly together by the strong nuclear force, manifesting as force-carrying particles known as gluons. And to the best of our current understanding, and it would be a very exciting day if we found evidence that this is wrong, quarks and gluons are it. They are fundamental particles that can't be divided any further. The quarks and the gluons and their interactions are encoded in what's known as the standard model of elementary particles. The framework was put together in the 1970s, and it contains just 17 fundamental particles that you see here, and it describes 3 of the 4 fundamental forces, notably excluding gravity. So you see here the matter particles, the quarks that I mentioned before, the electron and its neutrino and their heavier cousins, and the force carriers of the 3 fundamental forces that are included in the theory, the gluon, who we met before as the force carriers of the strong force, photon for electromagnetism, and the W and Z bosons for the weak nuclear force. And you might also recognize the Higgs boson, which was the last remaining piece of this puzzle that was discovered in 2012 at the Large Hadron Collider. Now this theory, which is built on principles of symmetry and can be expressed, extraordinarily elegant way on the front of my mug here, is really an extraordinarily successful description of the matter in our universe. It's withstood almost every experimental test. It is, quite frankly, the best theory of the matter in our universe that we've ever had. It describes matter at all scales, from the structure of the proton at the most fundamental level, all the way up to the structure of the elements built from protons and neutrons. You recognize the periodic table here, the components of the different materials that we interact with, through to nuclear reactions at a cosmic scale, like those inside the sun, to those used for energy generation and for medicine in nuclear reactors, all the way to the most dense known objects in the universe, the dynamics inside neutron stars. And standard model calculations are important not just to understand this emergence of complexity in the universe, but they're important to constrain physics beyond what we understand. So for example, dark matter, which we know makes up most of the mass in the universe, but is not described by anything in the standard model. But to deduce the properties of dark matter from its interactions with the nuclei in our detectors, we need to know about the standard model physics of the detectors themselves. So the motivations of this type of research are really, firstly, to understand from our most fundamental, our most basic physics theory, how the universe is built, but also to find where our understanding breaks down, those little edges like dark matter that give us hints that there's physics beyond what we know. So calculations within this framework, within the standard model of particle physics, even though the theory is so elegant, are extremely challenging. We can't sit down and calculate something like the mass of the proton or aspects of its internal structure by hand from the standard model. We don't know how to solve the equations. What we can do, however, is we can put the theory on a computer and we can solve it numerically. And just to give you an idea of the massive scale of these numerical calculations, something like 10% of open science supercomputing in the United States goes towards these sorts of studies every year. The types of calculations I'm discussing take something like 10,000 years on a good desktop computer. And of course, we don't use desktop computers. We use the most powerful supercomputers in the world. But the studies are still computationally limited. So the goals then of using machine learning and artificial intelligence for these sorts of fundamental physics calculations is then, of course, clearly to enable physics studies that are just not possible using existing algorithms and existing computers. The challenge of applying machine learning and AI to these sorts of problems is that we need algorithms which have guarantees of exactness. We are trying to exactly make predictions from this known physics theory. So we can't afford to have uncertainties introduced through inexact algorithms. So let me give you an example. One of the big computational challenges in these sorts of calculations is a sampling problem. We need to generate a set or an ensemble of what we call field configurations that describe the background quark and gluon dynamics of the standard model. These configurations have a complicated structure built on Lie groups, but you can think of them for now just as images like the ones shown here, where we want samples of these images with a precise probability distribution. Configurations like these ones here, which you can see have correlations at some characteristic scale, are likely. And ones like this one, which is just random noise, are very unlikely. And so these should occur more often than these. So there's, of course, a very clear and immediate parallel between the sampling problem that I'm describing, which is one of the key computational tasks in these first principles physics calculations, with a problem that's had a lot of attention in the machine learning community. That is the image generation problem. So if you can design machine learning algorithms that will generate pictures like this, these are not photographs of people, these are machine generated images of faces. You can go to thispersondoesnotexist.com and see them. If we can design algorithms to generate pictures like this and not like this, which is random noise, maybe we can use a similar sort of approach to generate these field configurations that look like this and not like this. Now, so while there's a very clear similarity, there are also some very clear differences and some unique challenges in using AI for this sort of a task. So let's compare a benchmark image set for machine learning to a set of field configurations. The very first thing that we notice is an extreme inverted data hierarchy. By that I mean, in a benchmark image set, you might describe each image with something like 3,000 numbers, and there might be 60,000 images in the set that you can use as training data for your algorithm. In our case, each of these images is described by something like 10 to the 9 numbers, but we only have and we only want order thousands of samples. So this hierarchy is inverted. And what that means is that any sort of machine learning approach that needs training data will be very hard to apply to this sort of a problem. So we use approaches that can be self-trained. Another very clear difference is that in the example of generating pictures of faces, you want each face to look like a face, but there's no requirements on the specific distribution of faces, at least no precise requirements. In our case, each sample needs to be a good sample, but overall, the distribution of the samples needs to follow a very precise probability distribution in a way that can be guaranteed to be exact. So instead of each image having meaning, it's the distribution. There are other differences in a picture of a face. Local structures are particularly important, like a nose or an eye in the image. In the field configurations, it's long distance correlations. And then finally, and maybe most importantly, there are big differences in the way symmetries feature. So on an image, okay, you have a translation invariance in the frame, whether the face is on the left or the right of the frame, it's still a face. But in our case, there are complex physics symmetries that feature, and the generative models need to be invariant to those symmetries. So what we find very quickly is that out-of-the-box AI tools are not appropriate for this sort of a problem, and we need to develop custom AI for physics from the ground up. And constructing these sorts of custom architectures for physics is one of the foci of our new Institute for Artificial Intelligence and Fundamental Interactions that's just getting started up in the Boston area this year. So what we need in these custom architectures is mathematically provable exactness in sampling, and we also need to be able to encode complex symmetries precisely. And just to give you some intuition on why it is just so important to precisely encode the complicated physics symmetries into our architectures, you can look at the cartoon I'm showing here on this slide, where if this is a distribution we're trying to model, and you can see there's a symmetry along one of the dimensions here, it's invariant along that dimension. If your model includes that symmetry in a baked-in way, then all you need to try to model is this simpler distribution here. If it doesn't, then you waste a lot of effort trying to mock up the fact that you have that constant direction. And especially when those symmetries are in very high dimensions, it becomes impossible to train architectures like this, whereas this is still tractable. So we have in fact developed architectures with these sorts of properties from the ground up, and I'm going to avoid going into really gory detail here, but here's an illustration of what some coupling layers in our custom architectures might look like, where you can imagine these as being variables on circles in the simplification of our case, and the architecture drawing in information from nearby variables in a very complicated way in order to preserve all of the symmetries exactly. I'll also show you an example of the effect of using this sort of a machine learning algorithm. So this figure here shows the cost of generating these samples, these elements of this probability distribution, these things that look like images, using conventional approaches and using one of the AI algorithms that we developed for a toy model. So you see here on the vertical axis the cost, and on the horizontal axis how that cost scales with one of the key parameters of the theory. You see that the conventional approaches here in orange and gray, the cost diverges exponentially badly as we change this parameter on the horizontal axis. Whereas for the AI algorithm, the costs are very close to flat. They are orders of magnitude more efficient than more conventional sampling problems, more conventional sampling approaches for this problem. So this is really a proof of principle success for these sorts of approaches, but there's still significant work needed to scale these sorts of tools to the scale of state-of-the-art calculations on the world's biggest supercomputers. And of course, the hope is that through these approaches, we'll be able to discover new things about the universe that are currently just computationally intractable, even on the most powerful computers in our time. Thank you very much.
Thanks, Phiala. That was brilliant, really fascinating. I love the combination of the sort of the biggest mysteries with the very smallest, most sort of complex things. That's really, really great.
Oh,
so,
my pleasure.
So starting with mysteries, what is the biggest, deepest, or most important fact about the universe that you hope this approach might one day be able to uncover, sort of further down the line?
Yeah, so really some of the big mysteries of the universe, I'll give you two examples. One is how you go from our most fundamental basic theory, this standard model of particle physics that describes what we think are the most fundamental particles in nature, how you go from that theory all the way up the scales of nuclear complexity to, say, chemistry, to nuclear physics. So we're just starting. A few years ago, we did the first calculation of a nuclear reaction, actually the first nuclear reaction that happened in the first microseconds after the Big Bang, from this fundamental theory, but there's a long way to go. So that's the first, the emergence of complexity in nature. Mm. And the second is some of these big questions about the physics beyond the standard model. So dark matter, for example, we're looking for dark matter. And what we haven't yet found is evidence in detectors here on Earth of dark matter. So you're trying to constrain what it is that's causing this difference between what we observe in the universe gravitationally and what there should be if there wasn't dark matter is a massive challenge. And so understanding better how different models of dark matter, so different hypotheses about what dark matter would be would affect our ability to detect it, can help us find more evidence and more constraints on dark matter here on Earth.
Fantastic. And then, I mean, yeah, staying with dark matter, I just love it. I love that that's the biggest mystery there is, and we're all sort of flailing around. If we find some sort of clues about how it fits into the standard model, or if it even means a new model's required, how will that change our understanding of sort of the fundamentals of how we exist, or where the universe came from?
Yeah, so one thing that's very clear is that the standard model works extraordinarily well, right? It's withstood almost every experimental test. And there's just a few hints, like dark matter being one of them, that give us a deviation from the standard model. So one thing is very clear, that whatever the more fundamental theory is beyond the standard model, it needs to include, at least as an effective theory, the standard model inside it. So essentially, we're not going to rewrite everything we understand. We're going to expand what we understand. You can think of it much like being classical mechanics before quantum mechanics was discovered. That still works at the relevant scales. Classical mechanics is not wrong. It will still predict, when you throw a ball where it will land, but you discover more.
Great. All right. Thank you. And in terms of machine learning, so you're looking at the face generation AI. I mean, I love that site. I follow the Twitter account that pumps out those like almost perfect faces. But like even with that one, with its sort of relatively small number of things that could go wrong in it, there's always like eyes in the wrong place, or like bits of head coming off. How do you know that those sort of errors aren't wrapped into your machine learning models for these bigger, more complicated questions?
So in our case, we design a different sort of algorithm, or an algorithm with slightly different features, because what we need is guaranteed exactness in this probability distribution. Now, what that means is that what the machine learning algorithm spits out, now it won't be quite right. It won't be exactly this distribution that we want. And so then there needs to be a mathematical way to correct for the fact that your distribution is not exactly right. One of the advantages that we have here is that in our problem, we do want every single picture that you could possibly make. It's not like we only want the faces, and if it's not a face, then it's bad. We want every image, even the ones that don't look like images at all, just with different probabilities. And what that means is if you get an image with slightly too high a probability and you know it's too high, you can downweight it. Or if you get one with too low a probability, you can upweight it. So there are ways of correcting for the fact that your distribution is not exact. And some of those ways, basically we can do them because we also have a very specific problem where that's possible.
Great. Okay. And in terms of machine learning, so applying to this first level of physics, is it opening up new avenues of research elsewhere in your field that haven't really sort of been explored yet, that you're excited about?
Yeah. So this idea of applying AI and machine learning tools to fundamental physics is really, on the theory side, it's fairly new. On the experimental side, experimentalists in physics have been using machine learning for decades now. And it's a massive component in, say, the triggers at the Large Hadron Collider. But on the theory side, these ideas of encoding fundamental physics principles, so things like symmetries that I talked a little bit about, but also guarantees of exactness, specific limiting behavior directly into the models, this is a fairly new endeavor in some of the fields related to mine. So this is part of why we've developed this new institute. We call it IAIFI, the NSF Institute for Artificial Intelligence and Fundamental Interactions, is exactly to develop these sorts of approaches that we call ab initio AI, so AI squared, where the idea is really to bake these sorts of fundamental physics principles into AI and develop it from the ground up. So this is rapidly developing, and we expect to see a lot more over the next 5 years or so.
Fantastic. And maybe the last question is, how will this sort of theoretical physics research, how is it going to mesh with experimental research down the line, maybe sort of next generation of particle colliders or anything like that?
Yeah, so the situation we have in particularly the standard model calculations that I was describing is that there's a large class of things that we know in principle how to calculate, but we simply just don't have enough compute to do it. Some of these aspects of nuclear physics correspond to what I was talking about. And so, of course, the ways we discover new things about the universe is you make a prediction from your theory, and you measure the same thing experimentally, and you compare, and you look for differences. And so if you can't calculate the theory part, then you have nothing to compare to find those small differences that are signals of new physics. So there's a very tight connection between what we're doing to say, understand the theory of the nuclei in the detector of your experiment and your ability to use that experiment to determine what you're trying to determine. So it really goes hand in hand.
Great, thank you very much. That's brilliant.
My pleasure.